I took another link by mistake. I hope we will. Okay. Okay. Yeah, I think there was a. Can you hear me? Okay. Yeah, there was a problem. I was in another in another Zoom conference by mistake. I would like to ask you if you have any question to speak loud. I increase the volume of my speaker here such that I can see, I can hear your questions. And I can repeat to the audience here. And I would like also to tell you that Octavio Villarreal, my assistant, is here and will be joining the lectures with us. And reply to questions and in case he wants to reply. You can speak loud whenever you have a question, so try not to write to the chat, such that, because for me it's very difficult to manage many things at the same time, and I prefer this way. And Octavio, are you here?
Yes, I am here. So
okay, good.
Can you hear me well?
Yes, wonderful.
Okay. You want me to introduce myself?
Yes.
Let me put on my video so you can see my face. Hi, everybody. I'm Octavio. I work with Mickey. I've worked with Mickey for about, with Michele for about 4 years. I work in the same lab as him, the Dynamic Legged Systems lab. I did my PhD there in advanced robotics. And the main focus of my research has been quadrupedal locomotion using vision. I think that Mickey had one slide in his introduction. And as Mickey said, I'm also going to be here during the lectures. I will be there in Trento some days to also be there during the lab sessions. And I will be hosting the Python tutorial. So if you have any question related to the course or the labs, you can also shoot me an email. I think that it's in the first set of slides of the lectures of Michele. Otherwise, I can write it in the chat as well. And I hope you are enjoying the course. I think that you should also take advantage of the experience of Mickey. He has been working in robotics for a very long time. So I hope you all enjoy the course. And I'm here also to help and assist.
Okay, thanks, Ottavio. Now I would like to ask to you guys if you mind if I quickly go through the same slides just for the people online to follow up, because this is quite involved concepts. So I will quickly repeat whatever I said in the last 20 minutes. So in essence, in vision, in robotics, we have some stereoceptive sensors that are used to detect information from the environment, and they are mainly classified into passive sensors that, for example, detect radiation, light, like the most famous one are the camera and image sensors, and active sensors that use an external emission device and use a receiver to get information on the environment around the robot. And the main type of active sensor used in robotics are called time of flight sensors or structured light sensors. In case of a camera sensors, we can use them for measuring distance, or to detect a 2D image. We will see later on how to reconstruct a 3D map from the environment using two cameras. They are made with photosensitive elements called pixels that transform light into electric energy. This light is directly converted into voltage or current proportional to the light intensity, and mostly these sensors are grouped into big arrays of millions. So there are millions of pixels, and that's why we talk about megapixels when we talk about cameras. And a camera also contains other elements like a shutter, lens, and preprocessing electronics. The measurement from the camera follows the projective geometry, and the advantage of a camera is the high resolution. The disadvantage is they don't work properly in absence of features. So whenever we want to reconstruct a 3D feature, the 3D image, we need to match some features between the two cameras that we are using, and we need some computer vision tools to reconstruct the 3D data. But before going in the task to compute a 3D map, we need to understand how a 2D camera projects the 3D world into a 2D image. And for doing so, the most famous model in computer vision is the pinhole model that represents a perspective projection from the 3D space to the 2D space. And we can see the camera as a barrier placed in front of an object that allows only some rays to enter through the barriers and project onto the a photographic film or the camera sensor. And the image that we obtain is flipped. And if we consider this is the aperture, the barrier aperture, that is the pinhole, and this is the camera center, this is going to be the focal length, and this is the camera plane or the image plane of the camera sensor. And we can say that there is a one-to-one mapping between the object and the image. Without a barrier in place, every point on the image plane could be influenced by the rays emitted by every point of the 3D object, and we will not able to see a sharp image, but just a blurred one. And we see that this triangle composed by the pinhole and the point on the object and point C is similar to this one. In theory, only one photon should pass through the aperture, but in practice, the aperture is finite. So if we reduce the size of the pinhole of the aperture, we get a sharp image, but it starts to be dark because a few photons pass through the aperture. But if you increase the aperture, the image gets blurred. So how people do, we use lenses, and lenses are elements that enable, for example, to focus light or the rays coming from this point are focalized into another point, and so we retain the same sharpness in the image while avoiding the image to get dark. So because we have many rays, and so we don't lose light intensity. And this property holds only for objects in specific distances that are in focus. This distance is called the depth of field and depends on also on the focal length of the camera. So if we move the camera, the lens position, we change the focal length and we change the depth of field. And here it comes to the way we project a 3D point into the 2D image plane, represented by a point P prime, while the 3D point is P. And this point is expressed in the camera frame, which is a frame which is on the image plane. And we project this 3D point to P prime point via a projective transformation. And if you look at the two triangles as before, the triangle made by this r, small lowercase r, and the distance z minus f, sorry, this is wrong. And the other triangle composed by the focal length and the capital R element, we can see that these two triangles are similar, and we can get a relationship that enables us to correlate the input point in 3D to the output 2D point P prime, this with coordinates X prime and Y prime. And this is a projection because we go from 3D space to the 2D space. But there is another clarification to do, and is related to the fact that digital images are expressed in a frame different from the camera frame C, that is called the pixel frame, that is normally located at the corner of the image plane. And then the other fact is that digital images are discretized into pixels, while the points in the image plane are continuous. So to convert to pixels, we need to consider how big is one pixel and consider an offset. How big is one pixel? We get with these parameters, AX and Y, while the offset of a camera frame with respect to the pixel frame expressed in pixel coordinates, it's represented by these two parameters, X0 and Y0. So X prime red and Y prime in red represent the coordinate of point P prime in pixel frame. Now, the size of the camera could be rectangular, so we can have more pixels on the length, right, rather than on the height. So we can capture this effect by setting two different parameters for vertical and horizontal components. And you have to note that all the points on the P prime line map to the same pixel, and that's why we have a projection. And the important fact is that this projection is a nonlinear transformation because we have to divide for the Z component. So we have a nonlinearity here. But what we want to do to be able to perform calibration of the camera is to have a linear transformation to map between P and P prime. And having a linear transformation allows us to represent this relationship as a matrix vector product, and that will allow us to perform calibration. And to be able to convert the relationship into a linear relationship, we need to change coordinates. So use another system of coordinates called homogeneous coordinates that is normally used in projective geometry. And the peculiarity of homogeneous coordinates is that if you multiply the homogeneous coordinate of a point by a scalar, the resulting coordinates represent the same point. So for example, a point xy in the Euclidean coordinates, if you want to get an homogeneous coordinate of this point, you can have a tuple like looking like this with xz, yz, and z that represent a set of homogeneous coordinates for that point, but also another set of homogeneous coordinates that represent the same point using, for example, the scalar 1, x, y, and 1. So as an example to the Euclidean point 1 and 2, we can represent it, we can associate two different sets, equivalent sets of homogeneous coordinates like 1, 2, 1 or 2, 4, 2. And the original Euclidean coordinates can be recovered by dividing the first coordinates by the last one. So this is set of coordinates for a certain point, and this is the associated set of coordinates for in Euclidean coordinate for the same point. Since we can associate whatever homogeneous coordinate we want, we select for the p prime point, we select this set of homogeneous coordinate, while for the p point, we select another set of homogeneous coordinate using the scalar 1. And if we look at the previous relationship expressing in homogeneous coordinate, we have, it simplifies to this one. And we see here that this relationship, it's linear, because if you can put it in a matrix form and obtain a linear relationship between the p point and the p prime point, both expressed in homogeneous coordinate. And this matrix here, it's called camera matrix. If we define the camera frame at the lens center and not on the image plane, the K matrix simplifies a lot and becomes like this. So this is what you find in many textbooks. But for the derivation, I prefer to use the other definition. Up to now, everything is clear. Also from the people online. Was a bit fast, the recap, but hope everything is clear. So, we have one problem here. So our camera detects the reality in the pixel frame, but what we are interested to is to relate this information in the pixel frame to the frame of a robot, like our base frame, because to do something useful, we need to understand where the points, how the points in the camera frame are mapped into the base frame. For doing so, we need an additional transformation between the base frame and the camera frame that we will use to map a point in the base frame into the camera frame, which is what we used in the previous derivation. Then, using the K matrix, we can map again. We can project this point in the camera frame into the P prime point in the pixel frame. So if we put everything together, we get a relationship, a linear relationship between the point in the base frame and the point in the pixel frame. Of course, we don't use this relationship, this direct relationship, but we use the inverse of this, because we get our sensor providing point in the pixel frame, and we want to obtain the same point mapped into the base frame to do the same, for example, visual surveying or 3D reconstruction of the map surrounding the robot. So these two matrices can be concatenated into a matrix MB that we call the calibration matrix. And the parameters that are inside the K matrix are called intrinsic parameters. While the parameters that are inside this other matrix, they are called extrinsic parameters. And so in the intrinsic parameters, we have, for example, the offset of the pixel frame, of the camera frame in the pixel frame, and the aspect ratio that normally are given by the manufacturer data sheet. You can get it. And the focus, you can change mounting different lenses in different positions. While the extrinsic parameters, they tell you where is the camera frame in the robot frame, in the base frame of the robot, and depends on the mounting. So if you for example, you mount the camera at the end effector, you'll have a certain roto translation to represent the position of that frame and the orientation of that frame with respect to the base frame. If you mount a camera on the trunk, you will have another one. And normally you decide to mount a camera, you don't know this roto translation. That's why you perform a calibration. When you buy your camera, you mount your camera wherever you decide to mount, then you need to do a calibration to understand what are these orientation and translation parameters. And if you want also the focus, but the focal distance, sorry, but in general, these parameters are given by the data sheet. And to perform a calibration, in essence, what you do is to do a least square minimization or solving a system of over the determined system. It is a system of equation that has more equation than unknowns, where the unknowns are the intrinsic or the extrinsic parameters that we want to calibrate. And to do so, people use a known pattern like a checkerboard that is a oh my God, really? And from the checkerboard node pattern, we have known points in the word or the base frame, for example, that are P1, Pn, and we have the same. We can see the same point in the pixel frame image, and so we can put together all these correspondences. Let's say we have n points, and we have n relationship with the M matrix. These are a set of numbers. Because you get the point in the word frame, that in the base frame that you know because you place the checkerboard at a known distance from the robot, and you have also the numbers due to the measurement of the camera in the pixel frame. So you can express the parameters as the same matrix product. You can work out the parameters and fill in this matrix that is called the regression matrix, and each correspondence gives us a free independent equation that you can use to solve for the unknown parameters. So if we have, for example, 11 unknown parameters, because we have 5 intrinsic parameters and plus 3 extrinsic rotations and 3 extrinsic translations, it means that we need at least 4 points, because 3 times 4 makes 12, bigger than 11, to solve this. In reality, because measurements are noisy, we can get a least square solution that tries to minimize the residual, taking more measurements. So we have more than 4 points usually. And if we put this in a big matrix form, we can compute the parameters to the pseudo inversion of this regression matrix Y. Everything is clear, more or less. Did you understand how calibration does? It means taking many points of non-correspondence between the base frame and the pixel frame, and then get the parameters performing a pseudo inversion. Then okay. Let's do a simple example of how much bandwidth we waste. We see here that this is IQ Real Robot. And this is our robot that is still operated from a user that is seeing whatever the robot sees with a camera feedback. And it's picking up objects, moving them, and it's the feedback from the robot. It's creating a virtual reality environment that is used by the user to teleoperate the arm to pick up the object. But let's see how much bandwidth do we need to transfer an image. For example, if you have an image, very small one, like 576 pixels height and 768 width, then we can compute how many pixels we have for a frame, doing a simple multiplication. We can encode this pixel with 8-bit. For example, in grayscale, we only need 8-bit for each pixel to encode the grayscale intensity. And we need to multiply by the frequency that we want to transmit this frame, which should be for human at least 25 hertz. Otherwise, you see the scattering image. You see an image that is not fluid. And if you do this multiplication, you can see that you can easily get, for a very low quality resolution image, you can get to 84 megabytes per second. This means that you really need a high bandwidth to transfer an image, and people usually employ compression algorithm to reduce the amount of information that we want to transfer when transferring images. Everything is clear? Okay, so now we can go to the last step. We know how to map point from 3D space to 2D image. And we want to recover the information on the depth, on the distance between these cameras and the environment. And to reconstruct 3D scene from the 2D camera's image, the most common method is the stereo vision, that consists in getting the depth information, the distance information, using the concept of triangulation. And you can think about stereo vision as, do you have an idea how stereo vision works? Do you have any insight on that? What happens when you go to the eye doctor and he asks you to look a pen, and you close one eye on the other eye, and what you see when you are close, you see your finger, and you close one eye or the other eye, and you see what do you see? exactly the finger moves. There is one eye that doesn't move the image, is the dominant eye, while the other one, you see the finger moves. And this is exactly the concept of binocular vision that allows us to reconstruct the sensation of 3D, the perception of the 3D world, using two eyes that detect both a 2D image. And stereo vision is exactly the same as binocular vision. And the idea is, as we have the eyes separated by some distance, we don't have one single eye. We have, I don't know, the eyes separated. And in some animals, the eyes are very far away, or in other animals are more close together. Then this separation allows to get two different images, and from the difference between these two images, that we call the disparity map, we can get we can reconstruct the depth information. And the disparity map, the values of the disparity map are inverse proportional to the depth of a corresponding pixel location. So for every pixel in our two images, we have a difference between these 2 points, and according to the difference, we can get the distance. So think about, for example, we have the two cameras, one on the left and one on the right. They are separated. They have two different image planes, one for each camera. And these cameras are located at a distance called B, that we call a baseline. And the same point P is captured in both the image planes, and creates two blue points that have a different distance from the camera center, that is called XL and XR. XL for the left camera and XR for the right camera. And the difference between XL and XR is called the disparity for the point P. And we can put this point on the other side and see the difference, the disparity as this segment. And we see that this triangle is similar to this triangle. And we can relate the depth Z to the focus, that is the distance between the image plane and the camera, and to the disparity with this relationship. So we have Z over B, which is the base, is equivalent to the height of this triangle, which is the focal length, over the base of this triangle, which is the disparity. And rearranging this, we get the distance proportional to the disparity, because as we know, the focal length is defined whenever we mount the camera, and the baseline also is defined whenever we place the two cameras. We can decide where to put the two cameras. In general, the stereo cameras, they come together. So it's a single package. They already have two cameras. You saw an image before of the stereo camera. So the baseline is predefined. But as I said, we need to, to calculate the depth, that we need to know the disparity, and we need to understand the correspondence of these two blue points. And these correspondences of features of points are called matches. And you can see from these two images that these points are correspondent to the same point, but in two different image planes. And once we have this correspondence, then we can derive the depth for each point. And if the feature matching is wrong, then we also know that we are not able to properly estimate the depth or the point. And this is one of the main shortcoming of stereo cameras. Whenever, for example, you are looking for a white wall with a stereo camera, there are no features or uniform colors features uniform color planes without any roughness, without any detail, so that the stereo vision algorithm, it cannot associate this correspondence between the pixels, between the two images acquired by the two cameras, and 3D reconstruction is not possible. And the baseline distance is strongly related to the maximum, so the maximum detectable depth range is proportional to the baseline and to the sensor resolution. And the baseline tells you what is the area where you can reconstruct the 3D image. And there is a baseline, for example, for robotic application of around 6-7 centimeters, while for self-driving cars, it's around 14 centimeters. And you see here that if the two cameras are more far from each other, you have a bigger blind zone in front of the robot wherever you cannot reconstruct. In particular, in our robot, for example, we have a problem because we are using some sensors, some stereo cameras that have a minimum distance of 40 centimeters. So closer to 40 centimeters, closer than 40 centimeters, the camera is not able to detect to build the 3D map. And this is a problem, for example, whenever the robot walks very low in height and is climbing stairs, and the camera gets very close to the stairs, and it completely screw up the image because it cannot get any information at that distance, and normally gets not a number. So we need to use techniques to retain the useful information from the stairs, from the previous acquired map. And we have problem of drift because this information gets old. So whenever you add frames, you're moving, you need to estimate your motion and to add new frames on top of each other and increase the knowledge of your map. So we will see this in the later slides. What drift problem of the drift and how can we cope with that. A software library that people use is the OpenCV library, and it's very common in research groups and companies. It's open source and is used for computer vision and also machine learning. It has more than 2,000 algorithms for computer vision, including the stereo vision one, and also face recognition, identify objects, and extract 3D models of objects, for example. And it supports C++, it's written in C++, it supports also Python, Java, MATLAB, many operating system, and but it keeps its good computation performances because of the C++ implementation. Sorry, I closed the door. Okay, I will do a short break if you want now, then continue 10 minutes break, then keep going. Okay. Here back. Okay. So yeah, it's an important point. Octavio and me prepared an assessment form. We put an announcement on the Moodle that it will be good if you can fill it in to give us some information on your previous knowledge, on what you are interested to, such that we can steer and we can tune the course, because it's the first time we do this course, so we need feedback from you to be able to better tune according to your needs. So if everybody is able to hear everything and see everything is right online. Okay, good. So let's go into talk about the next class of exteroceptive sensors. Again, they are used for distance or 3D reconstruction of the environment, and they are called time of flight sensors. And they are called time of flight sensors because they compute the distance, measuring the time that a pulse of a laser or another coherent light source or an infrared emitter takes to travel from the source to the observer target and back to the detector. And the detector usually is collocated together with the source, very close. What are used in time of flight sensors are coherent light sources that are light sources that have a single frequency beam, for example, in the case of laser, and they are very lightweight and they are unidirectional. So they have temporal coherence, single frequency, and also spatial coherence. This means that the rays, the beams, are parallel on long distances, while with diffuse light, you have a ball of 360 degrees sphere of 300 around the source. And this allows you to have a very sharp focus on very small areas that will not be possible with non-coherent radiations, and reach therefore very high resolution and very high power density. Sorry, not resolution, very high power density. And the fact that it's a single frequency, they also more easily to be filtered. And the round trip travel time provides the 3D position of the object from the sensor, using the speed of light and projection angle of the ray. So you get the laser reflected, and you are the receiver here at a certain angle. And the limitation on the accuracy of the sensor are based on the minimum observation time that limits the minimum distance observable, because we have a certain accuracy in the way we detect the time of flight, because the speed of light is very high. So in theory, we could use this sensor only for very, very long distances. But we will see there are other tricks like modulation and demodulation that allows us to measure smaller distances even with this kind of sensors. And the kind of reconstruction that you do with these sensors is a point-to-point reconstruction. This means that to detect more than one point, you use mirrors. To rotating these mirrors, you change the emission of the laser or the detection of the sensor, and you can get more than 1 point sweeping this mirror around, rather than moving the detector or the emitter. And this is better because the mirrors are less prone to motion damage. And the most famous time-of-flight sensor is the LiDAR. The LiDAR is like a radar, but the difference is that a radar has a bigger wavelength, like the order of centimeters. We will not be able to discriminate resolution under 10 centimeters, I'd say, if we use a radar. And while the LiDAR is on the ultraviolet frequency range, and where the wavelengths are order of microns. And the LiDAR is used commonly used to take to make high resolution maps, normally offline, and uses lasers, laser waves, and these laser waves can be reflected for very small objects, so very high resolution. And these LiDAR are the sensors that are used, for example, in self-driving cars to create a map of environment, or, as I said, offline to, for example, create a very accurate map of a warehouse, of an oil platform that is used in a following moment for a mobile robot to explore or to localize himself and to check. For example, a very interesting application that we got asked to develop from the region of Valle d'Aosta was to explore the tunnels or the water tunnels that are used to fill up the dams, the lakes, or that are used in the hydraulic power plants. So inside the mountain, there are these kilometric long tunnels that are needs to be checked every year for water leaks or landslides that could block them. And this inspection cannot be done by humans anymore because it's very dangerous. It's very dangerous. So the new regulation requires that mobile robots or legged robots are used to explore these tunnels. And you having a map of the tunnel, you can check, comparing the map with respect to the previous year, if there was some problem in the tunnel or some damage. So having 3D maps is very important also for diagnostic and inspection. Then another time-of-flight sensor that is used is who is there? Are they closing us inside? No. I just don't know. Okay. The other kind of sensor that is the time-of-flight sensor. It's the structure light sensors. Yeah, and these sensors are we are still talking about the LiDAR class of sensors, time-of-flight sensors, and the advantage of these sensors is that they can cover large distances because of lasers, and they provide accurate depth estimation. The coverage is only limited by the power of the laser. And in case, as I said, of shorter distances, the frequency amplitude modulation could be used as strategies to have a measurement that is not related only on the speed of light, time of reflection. And the advantage is that Another advantage is that they are not sensitive to light conditions, so they are perfectly suitable for outdoor application. Actually, they are mostly used for this kind of application. The disadvantage is that they are very, very expensive. There's around 24, 25, 30,000 euro each. And they have scanning difficulties with the reflective surfaces like, I don't know, mirrors or stuff like that. And they have low resolution with respect to 2D cameras because the kind of map that you get from this sensor is very sparse. So you get point, but as long as you are far away from the source and your accuracy of pointing your mirror it's limited, you get sparse map very, very far away. While the other kind of active sensors is the one based on structured light. And what structured light means? It means that this kind of sensor, they project a bidimensional pattern to estimate on the object, to estimate that distance information on the whole object. So the main role of the projected pattern is to establish these correspondences between the known pattern and the camera measurement. You remember the feature matching problem of the stereo cameras. Here we don't have this problem. And the variation on the pattern that we project and we receive on the receiver with a certain variation encodes the information on the depth of the point of the object we are measuring, and this information can be recovered with a triangulation strategy. And this kind of sensor, for example, are the Kinect, the Asus Kinect sensor. And the advantages with respect to stereo camera is that they don't get confused on uniform surfaces because they don't have to perform feature matching. They are cheap, lightweight, small, and they consume very small energy, very low energy. But the main disadvantage of these kind of sensors is that they are very sensitive to light condition, because the infrared, they are mainly infrared sensors, so they are not a single very focused laser beam, but they are diffuse light. So they are only used for indoor application. And even in indoor application, if you have some light coming from the window, for example, the infrared component of the ambient light completely can affect the measurement of the sensor. And as I said, Kinect is an example of this sensor, and normally a Kinect as a camera, 2D camera inside, plus the infrared emitter and an infrared camera, so 2D camera plus an infrared camera. And the range is between 50 centimeter and 5 meter. The cost is very low, below 100 euro. And the depth for each pixel of acquired by the RGB camera is associated with the value of the depth for that pixel coming from the triangulation of the infrared pattern. And by post-processing, you can do many nice things. For example, you can track human motion. You can attach to the body of the human some markers and define a model for these markers. So you can acquire, find a relationship between these markers. And in a software, you can check the motion of these markers and reconstruct the motion of the humans from the markers. At IIT, we have many experiments with this kind of stuff, especially whenever we want to study the human motion. So understand how humans perform grasping or move in the space, or people that are injured, how their walking pattern is affected by their abilities of walking, or how are they improving. So even detect the improvement in the motion because of some physiotherapy protocol. So this kind of evaluation can be done using a simple Kinect camera. Other very simple post-processing of images, they are contour or edge detection. And in this case, you, in essence, from gray image, you get a gradient of the light intensity and use this gradient, setting a certain threshold to detect the change in light intensity. And usually whenever you are changing light intensity, you have you can get the contour of the object, the edge of the object. And once you have the edges of the object, you can recognize shapes and classify, for example, different kind of objects. And to do so, again, for edge detections, you can have many algorithms available, many algorithms available in the OpenCV library. If you have questions, everything is clear to now. An important point in computer vision is to evaluate the motion of the camera, looking at the changes in the camera images. And this is the task of visual odometry, which is the process of estimate the pose of a camera attached to a vehicle or a robot, examining the changes that this motion induce in the image. So pose after pose, you can extrapolate from the changes in the images the motion that the camera is doing, and you can use that to estimate the motion of the camera itself. So for each image sequence, you need to do the feature detection, feature matching, and you can extrapolate the motion of the camera afterwards. The problem of this incremental motion measurement is that there are errors that accumulates over time and generate a drift. So the motion that you estimate is not whatever you really it really happens, but is affected by a systematic error that accumulates with time. And therefore, one strategy that we use in robotics is to fuse different sources of to the estimation of motion that are relying on different principles. So the visual odometry could be one way to estimate the motion. We can correct, use a LiDAR to correct this drift in position. Like every once in a while, we find where are we in the where the object is in the space with respect to the robot, and knowing the exact position, we can correct this drift that was accumulated by visual odometry. We also can use the IMU because we know, for example, the angular velocity and the acceleration. We can employ this because if we see an angular acceleration or a linear acceleration, if we remove the gravity, we can, as I remember, we can double integrate this and obtain an estimate of the position. And we also have leg odometry. To estimate leg odometry, give you a simple example. I don't know if you can see me. So I have my trunk, and if I have a contact, the point in contact, the feet in contact with the ground, I can estimate the orientation of my trunk, considering that my feet on the ground are not moving, and using the measurement of my joints. So using encoder measurement, considering that the point in contact on the ground, like the feet, are not moving, we can estimate the orientation and the linear position of the base of the robot, for example. If I have the base frame attached to my body, to my trunk, I can estimate its position. And of course, this works only if you have contact points. If you are jumping, this doesn't work. But fusing all of this in as inputs for a Kalman filter, extended Kalman filter, you can get a more accurate estimation of the states that are not observable. That, if you remember, are, for example, the linear position and the linear velocity. For example, the leg odometry is affected by the fact that there is a mechanical compliance in the legs. So if the legs deforms, I read a wrong, I estimate a wrong motion in the base because of the deformation. And then once you have a nice state estimation algorithm, you can walk around and you can acquire a map. How do you acquire a map? You every time instant, you acquire a set of 3D point. So you get your triangulation with your stereo camera, for example, or with your LiDAR. You get all this 3D map, but you need to merge this 3D point cloud with the one that you will acquire the next sample. And in the meanwhile, you could have moved. So you need to consider, you need to exploit the state estimation algorithm to know how much did you move between one acquisition and the other in order to be able to sum up these point clouds and gradually build up the 3D map. And how do you put together these point clouds? We can have different representation of building a 3D map from the point cloud. One is the octomap, which is called occupancy map as well. And this map is very, it's convenient if you want, for example, to get information also in, let's think you want to, you have a table and you want to see under the table. This kind of map that discretize the environment in voxels that are little cubes and gets the occupation of the objects in the environment, the real occupation of the object in the environment. While the elevation map or height map, it's called a 2.5D map because it gets only the height. So if you want to look under the table, you cannot do with this kind of map. So because to every point in the XY plane, you associate the height, but you cannot see like situations wherever you have a hole under your pallet. For example, you want to work on the pallet and you have a hole under the pallet, you don't see this hole because all the points under the edge, so the points on the pallet are just you can get only the height of the height, a scalar field on the surface. So you don't get any 3D information under the for each XY component. Yeah, this is the height map, and we usually employ the height map for locomotion. For example, you can use it to detect the step and adjust the swing to avoid the step and walk over the pallet, for example. Then the last class of distance sensors that can be used in the automotive field, in the industry, whenever you want to detect the presence of an object on a conveyor belt, for example, are proxy sensors. They are used to detect the presence of object in a specified interval of distances. They typically have an on-off output, so object present or not present, and they have a short distance range. These proxy sensors are based on different technology. One of them is the ultrasound. It's very low cost, and you usually put an array of this sensor around, for example, a mobile platform that needs to move around and avoid hitting obstacles or hitting objects. And so this is a typical application of these kind of sensors. Otherwise, you can have inductive-based proxy sensors that are the ones, for example, that you have whenever you want to detect an object on a conveyor belt, and they are based on the variation of inductance due to the presence of a metallic object. So whenever you are close, you have a permanent magnet that generates a magnetic field, and these magnetic field lines are modified by the presence of this ferromagnetic object. Whenever it's approaching, shifts the magnetic lines, and these magnetic lines will couple differently in a coil and will create an induced voltage that is positive or negative if the ferromagnetic object is getting close or getting far away. So we get a voltage here. And they have low sensitivity, and the detection range is only a few millimeters, because then the magnetic field, it becomes very weak. The other last one kind of proxy sensors are the Hall effect sensors. And they are usually, I think, made with crystals, and their output voltage instead is directly proportional to the magnetic field strength. So before was related to the field variation, magnetic field variation. Here is proportional to the magnetic field itself, and it detects a strong magnetic field whenever the ferromagnetic material is absent, so it's far away from the sensor, and a lower one whenever it is close. And these kind of sensors are used typically whenever you want to synchronize a rotating part, like for example with some other elements, like in a combustion engine, where you want to synchronize the spark for the ignition to the angular position of the motor shaft, or in brushless DC motors, we will see to detect the position of the rotor, or the permanent magnet of the rotor. The other way is to implement a proxy sensor using capacitance, and this proxy sensor based on capacitance variation can detect all kind of material, even solid and liquid, and because they are based on the variation of the capacity induced by a surface that is close to the sensor. So one of the armature of the sensor is on on one armature of the capacitor, it's on the sensor, the other one is on the object to be measured. And the detection range again is very small, a few millimeters, and the response depends on the material, but can be very precise if tuned for a particular object. And this is the last slide of the exteroceptive sensor part. And if you have any question about that. Otherwise, we move to next part. Octavio, can you see the slides?
Yes, I am able to see.
Okay, so I don't have to reshare the screen. That's great. So this part, it's about signal processing for robotics. I provide you some brief introduction to some useful concepts that you might want to use when designing your system to control your robot. And these concepts are related to filtering and to sampling, quantization, and possible issues that you can have whenever acquiring data from your robot. And if you consider how controllers are implemented nowadays, they are implemented on digital machines, on computers, on microcontrollers. And this means that, for example, this is a typical sketch of a closed loop control system. We will see this more in detail in the control section topics. And in closed loop control system, you have a reference to be tracked. You have a measure of the control variables that is your output that you want to control. And this, you normally have a system to control that is a plant that generates the control variable, for example, the position of your link. You have an actuator that applies your control action on the plant, and the object that decides how to command the actuator is the controller. That usually compares the reference with the measurement of your control variable, and according to this error between the measurement, the reference, and the output of that you want to control, it decides an action that is the control variable to apply to the actuator. And the digital implementation of the controller implies that usually this controller it works at low power. So the plants, our robot require a high power control action, while the output of a controller is an informative signal that is in general an electrical signal, but it is a low power. So our control variable needs to be amplified before being applied to the actuators, while the actuator usually converts the low power signal into a high power signal, making the control signal compatible with the power plant, sorry, with the plant input. For example, the torque of input of our robot. And while the control variables are usually measured via sensors, and they convert, we saw that physical quantity into a low power signal readable for the controller, for example, an electrical signal. And to being able to adapt this low power world with the high power world of the real system, we have two fundamental and also to adapt the fact that the real system is living in a continuous world. So we have the torque is continuously changing and not only at some time instant, while the controller is running at a certain frequency. I can have a knowledge on the environment and can apply an action on the environment, on the robot, sorry, at a certain time instance. And to have this in connection between these two words, we have two elements. One is the analog to digital converter, and the other one is the digital to analog converter. And you see this, the previous closed loop system differently sketched, and all these signals are synchronized with the controller on a period, according to a period TS that is called sampling time. So the controller reads the sensor at a sampling frequency, at a certain sampling frequency, while it applies its action at a certain frequency. And we have a digital to analog converter whenever we want to convert the digital signal coming from the controller into an input for an actuator, and we would have an analog to digital converter when we want to, as we saw, convert our sensor output into a digital signal. Yeah, so this is what I just said, and the time interval wherever this sampling happens are called sampling instance, and you see here the different kind of signals. So the controller output is a digital signal. Then we have we will see what is this, and you have an analog signal on the output. So the analog signals are signals that can vary continuously in their magnitude and with time, and they are called continuous time signals and have this kind of shape. While quantized signals are signals that can assume only a limited number of values and can be represented by, for example, n bits. So, you know, with n bits, you can describe 2 to the power of n discrete levels. And the minimum variation, we saw that is called the quantization level Q. So the minimum variation your signal can vary, it's a quantization level. Then sample signals are analog signals that are evaluated only at the sampling time instance. And sample signals are also called discrete signals, and they have continuously varying amplitude, so they can assume whatever value, but they are evaluated only in some moments. And this is the way you define a sample signal. X of t is the analog signal, and the sampled version of the analog signal is x k of ts, because k varies from 0 to whatever number, and it's multiplying this time interval ts for 0, 1, 2, 3, 4, and so on. While digital signals are is a quantized signal that is sampled. So it's something in the middle between these two. So we take a quantized signal and we sample it, and we obtain a signal that can assume a limited number of levels of output levels, and is also evaluated at the sampling interval. And in general, whenever you want to understand what is the number of bits that you need in your A to D converter, you need to consider the range, the output range, and also the quantization level that you want. And with this formula, you can, in essence, obtain the number of bits that you need. So, for example, commonly used AD converters for a robotic sensor are 16-bit, and you can discriminate. You can do you can compute the inverting this relationship. How much is the quantization level that you can measure? For example, for a 0.10 voltage or 0.5 voltage range, which is typically what you have in your acquisition board, the range that you have in your acquisition board. Everything is clear? So if we look at the analog to digital converter element, it performs both sampling and quantization, where sampling converts the time varying voltage signal into discrete time signal. The quantization instead replaces each number with an approximation, each real number continuously varying signal with an approximation from a finite set values, and giving output as output a digital signal that we call XQK of TS, that is codified with a sequence of bits. While the digital to analog converter, it performs the reconstruction. This time we want to reconstruct the analog signal to provide to the actuator that in inputs wants an analog signal, starting from the digital sequence of samples coming from the controller. And this is realized by the component that is called zero order hold. Did you ever heard about this? So zero order hold is a component that maintains constant the input received at a certain time interval along all the sampling time. So if you have our digital signal here, after passing through the digital to analog converter, we get this. So the digital, the value of the digital signal at some time interval is kept constant all the time interval. Then a second digital, the value of the digital signal comes and is kept constant along the interval. And you get this reconstructed analog input, analog output. What is the problem, in your opinion, with this reconstruction? Staircase function. And what the staircase, what causes? Apart from vibrations, but let's say we are sampling quite fast, and the mechanical system is slower, then our sampling frequency is not responding to these stairs. What is the problem of doing this, keeping constant? And why this is a problem for a control system? Yeah, but as I said, the time constant of the actuation of the system is very low with respect to this, so it's filtered out. We will see the next slide. One of the problem is the delay. The delay, we will see also in the control lecture, are creating problem in your control loop. Because when you close the loop and you have a delay in your actuation or in your sensor, this delay creates instabilities. The advantage of the digital implementation, by the way, is increased flexibility. I can code my control law, I can change it, I can try many different control laws without having to just changing a line of code, for example. While before, to create a controller, people had to use capacitors, resistance, and inductance, and they had to put them together to create a controller. So they were analog controller before the computer era, and this analog controller that you implement either using these electronic circuits or using valves and stuff like that. And the other advantage, apart from flexibility of digital signals, is that they are more robust than analog signal to be transmitted. So if you encode to digital, you can have a value that goes to between 0 and 1, where 1, I don't know, is 12 volts or 5 volts. And if there is an electromagnetic noise coming from the environment, from your cell phone, that couples and disturbs your signal, still the two levels are so far away that it's more robust to this, and it's less frequent that you have a change in your bit level because of external noise. But another problem that we saw in digital implementation is the quantization error. We already saw that. We can repeat quickly. Whenever you quantize a signal, we are adding an additive random disturbance called quantization noise, and because of the effect of quantization is that we cannot discriminate two quantities whenever they are closer than the quantization level, and the quantization we saw can be implemented by truncation or rounding, showing these two different patterns. And this random noise is usually a white noise uniformly distributed with a constant probability density equal to 1/q. So this is just the two probability distribution of rounding error situation and of the truncated truncation case. And here we come to the other issue of digital implementation, that are delays. And the delays are associated with the sample and hold, with the hold part of the sample and hold. And we can see that if we have our discrete signal, the average we have our reconstructed signal that is this one, And the average of this, which is a dashed line, it's an approximation of the original signal, that is this one. So we have a delay of half of the sampling time. And this delay can degrade performances, especially when your control law it's implementing a damping. We will see what is this, a damping controller, and affect the stability, because it creates a loss of phase margin in your control system. And this loss of phase margin you can evaluate, for example, at the crossover frequency of your system. And for a delay of sampling time divided by 2, it translates into a phase delay of minus omega TS divided by 2, where omega is the crossover frequency. Is it clear? So reconstruction creates delay and creates problem in the controller. Quantization creates problems in terms of quantization errors. And the last problem in this time is due to sampling, is the aliasing. And think about we have our signal that we want to sample, our analog signal, that has a certain frequency content. This is the plot of a spectrum of the signal that represent the frequency content. The frequency content, the spectrum is also flipped in the negative axis. I don't know. Did you ever see what the spectrum is? Fourier analysis is used to obtain this plot, and it tells us, in essence, what is the frequency content of our signal. And we see that here, for example, that our analog signal has a frequency content below a certain frequency B. And if we sample this analog signal and we do at frequency Fs, and we do a spectrum, we compute a spectrum of these sampled signals, we see that the spectrum of the sample signals is a repetition of the original spectrum of the original analog signals, and this repetition are shift of multiple of the frequency Fs. And if the sampling frequency is bigger than 2 times the maximum content of frequency of the analog signals, it's possible for these copies to be distinct one from each other. And this means that we can, from the sample signal, we can reconstruct the analog signal by, for example, putting a passband filter across the analog signal. And otherwise, if the frequency is sampling frequency is lower than 2 times the maximum content of frequency of an analog signal, these copies will overlap and create lower frequency component in the reconstruction that boils down to the phenomenon of aliasing. So here you see that what I said before, if you're able to sample twice then the bandwidth of your analog signal, then you can reconstruct the signal and there is no overlap. You can see this this example. What does it mean that low frequency component appears? So our cameras it's sampling our image at 25 Hz, but the frequency of our signal increase that represent the velocity of our marker on the wheel, and we increase the wheel speed, and we see that at some point before you can see again, it starts to seems like to rotate counterclockwise at low frequency. This is exactly what you see. It's called the stroboscopic effect. What you see in cars whenever you see their wheels in a video, they rotate backwards. And an important theorem in it's the Nyquist-Shannon theorem that tells us a sufficient condition to compute a sampling frequency that allows us to avoid the aliasing problem and make us able to capture all information from the analog signal of a certain bandwidth B. And is what we saw before. If a sampling frequency is bigger than 2 times the bandwidth of your signal, then we don't have aliasing. And rule of thumb is whenever you have an analog signal, you should be filtering with an analog filter before sampling to reduce the high frequency component according to the level of that you want that depends on the sampling frequency that you want to have in your acquisition board. And this anti-aliasing filter is an analog filter and usually is implemented with a RC circuit, so a resistor plus a capacitor. And the sampling frequencies that we choose for our controller should be a compromise within different goals. Should be high enough to avoid aliasing due to the Shannon theorem. Conservative is 10 times the filter bandwidth, the anti-aliasing filter bandwidth, but high enough also to reduce the delays due to the digital implementation, because we saw that the delays is half the sampling time. So higher the sampling frequency, lower the sampling time, and lower the delay, but not too small, because we saw in encoders that we can amplify the quantization noise whenever we compute the velocity, and also the computation time. So we need to be able to for example, run our controller at 10 kilohertz. We need to be able to have enough computing capacity to compute all the control law that could be complex in a very short time interval. Everything is clear? You want to do a break or continue 5 minutes more and then do a break? Yes, what? Okay, let's do 10 minutes break. Okay. Okay, let's start. If everybody's back, or should we wait? Okay. Yeah, seems like. An important element that we introduce whenever, for example, we want to reduce the quantization noise of the velocity computed by finite differentiation of an encoder. We said it was the low pass filter. And here we are not talking about an analog filter, like the one that is used for anti-aliasing, but of a digital one. So a filter that we can implement via software in our system to remove the high frequency component of our signal. In fact, an ideal low pass filter should keep unchanged the frequency. The signal should keep unchanged the signal in magnitude and phase inside the bandwidth of the filter, and attenuate massively the signal beyond the amplitude of the signal beyond the filter bandwidth, which is at the cutoff frequency. So if we do a Bode diagram of our filter, low pass filter, we see something like this. 0 dB, which means 1 in amplitude, for all the frequency range inside the bandwidth that we decide to be the cutoff frequency, and then an attenuation. In this case, is a one-pole filter, so 20 dB per decade of the highest frequency. This is a low-pass filter because passes only the low frequency and attenuates the high frequency. Did you see a Bode diagram in previous courses? How many of you? Raise the hand. Very good. Okay. Another class of low-pass filters are the Butterworth filters, and their peculiarity is that they have a higher order, so they have more than one poles in general, where the order of the filter is represented by the number of poles, and determines the order of poles, or the order of the filter determines how sharp is the frequency cut. And the price you have to pay for having more poles and a more sharp frequency cut is a higher phase delay. And the higher the order, the bigger the phase delay, close to the cutoff frequency. So you have a Butterworth filter of order 1, which is cutting, it's not very sharp, but then you increase the order and you see a more abrupt cutting. So if you want to be sure to remove everything beyond this frequency, then you want to use a higher order filter. In general, the gain of the filter, again, the relationship, the transfer function between output and input, it's 1, because we don't want to scale down our signal. We want to just remove the higher frequencies. And how do we implement in our code our first order filter, for example? So we start from the differential equation that represents the first order filter. We here have the input signal and the output signal filter, and this is the differential equation that represents the filter. Tau is the time constant, And if we do the Laplace, we computed Laplace transfer function in continuous time, we get that this expression where we replace the derivative with an s. I don't know if you ever saw that. And then the transfer function is the relationship between the output and the input, and this is the transfer function for a first order system with one gain. We will see this better in the control section. And the time constant of the filter is tau. So the time constant is related to the bandwidth of the filter. Actually, it's 1 over the bandwidth, and not really 1 over, let's say it's 1 over the bandwidth. We will see better this in detail. And the important thing is that to implement this by software, you need to implement this in discrete, and to implement in discrete, you need to discretize this differential equation and pass from a differential equation to a difference equation. It's just an algebraic equation. And in specific, we approximate the derivative with rapporto incrementale divided by the sampling time. And we working out this expression, we can collect yk, which is the sampling of the signal at the time instant k, while yk minus 1 is the sampling of the signal at k minus 1. So that the derivative is a finite difference of these two divided by the sampling time. And if you collect yk, you get this expression. And simplifying, you can get an expression like this, where we have something that is multiplied by our input and something else that is multiplied by the previous value of the output. And this something is, we call it beta, and as this expression that can be simplified like this. And higher beta, what does it mean? In this case, that our input will be more influencing the output, while a lower beta, it means that the input will influence the output less. So if I have higher beta, my filter, it's more reactive or less reactive. So it's filtering more or less. Yeah. Exactly. While with a lower beta, we have much more filtering. So the input variation is reflected slowly in the output. So let's say you have a step input, your output will increase slowly. Step input and your output decrease slowly. While if you have a higher beta, you have a step input and a prompt reaction. So you have less filtering. And the response, exactly what I was saying, will be faster or slower according to the beta. And we see that the beta is strongly related to the sampling time and to the tau constant. So, and the tau constant is related to the bandwidth. So you have the bandwidth that you want to achieve, you compute the time constant, and from that you can compute the beta, and you can implement this same line in your code, and you will see that your filtered signal Y will be a filtered version of your input signal U. Okay? Another thing you can use in signal processing in robotics is the mean or average. It's the same thing, or moving mean or moving average. And mean means computed arithmetic means that you compute it a posteriori. You need all the data available, and you compute the mean of all your samples by summing them up and dividing by the number of samples. But what is the problem related to this approach? Let's say you are collecting your input signal, you want to compute the mean. No, but yeah, if you could compute, you could keep, yeah, exactly. This is one problem, but the other problem is also that the number increase. So you're going to overflow, because sometimes at some points you will reach a limit of your description. Let's say you're using a double or an int, and you will have a maximum number you can represent. And this number will increase because you're summing up stuff, and at some point you overflow. To avoid overflow, usually use a moving mean, which means you compute the mean only of a subset of your full data set. You don't use your full data set. And the first element of a moving average or moving mean is obtained by taking the average of the initial subset of the samples. And then the next element is obtained by shifting this subset of one element. This means excluding the first number of the series and including the next one in the subset. And you can compute this way, wherever this is the moving mean of the kth element of the signal, considering a window of size m. And the moving mean is something like that. It's something like a filtered version of the signal. Let's see, this is the input signal, and this is the moving average, and tells you about the trend of your signal. So if you have you are interested into the average trend of your signal, let's say you want to know the power. You don't care about, you want to compute the power of your joint, but you want to know how much power you consume roughly in time, and you want to, so you take the absolute value of your power, and you have something like that. You want to know on average how many watts you need for your robot to, for example, size your battery. You want to size the battery, so you want the average power, and you can compute the moving average and plot it. And this is to smooth out short-term fluctuation, and I like the long-term trends, as I said. And the difference between with a low-pass filter is that this gain is different than one, so it's not one-to-one the input-output. And the implementation of a moving mean could be different. To save memory, you can use a ring buffer. As we said, we have a window, we have a buffer of elements, and then we remove an element. We shift the shift in the window means that we copy over all the element of one place from the last one to the previous one, then back to the first one, and we remove the first one from the buffer. And this for each step. Or we can implement it in a recursive way. Let's say we have a previous expression of the mean as a sum of element divided by k, and then rearranging this expression, we can have an expression for the moving average with respect to the previous value of the moving average at the previous loop, and this simple expression, it can be implemented. It's what we usually implement via software, because it's the simplest one and doesn't use any memory. And the new sample enters here, and we just keep a memory of the moving average in the previous sample. Another variation of moving mean or moving average is the weighted moving mean. And weighted moving mean, it means that we have in our window, wherever we sum up our samples, we apply some different weighting multiplying factors according to the position of the sample in the window. So, for example, we might have forgetting feature because we care more about the last acquired element than the past element acquired in the past. And more in the past, the more you want to have their influence becoming less in our signal. So with a weighted moving mean, we can scale down the weights and add some forgetting feature in our data. And the convolution of if you don't know about convolution, it's the output of a weighting moving mean is the same as performing a convolution of the last m sample points with a fixed weighting function that is, for example, this one. Denominator will always be the sum of the individual weights, and this is the expression for a weighted moving average or weighted moving mean, considering the last m samples. Do you have any question? Yep. There is an equivalence between the average filter, let's say, and the first order filter. I need to investigate this if it's possible to define an order for this or not. I will tell you next time. Yeah. Okay. I will quickly start the next topic in the last 15 minutes. That is about actuators. And Octavio, can you see the slides?
Yes, we can see.
So we quickly start this new chapter about the actuators. We talk about sensor until now, and we will review in this lecture, set of lectures, what are the kind of actuator we use in robotics. We will talk mainly about electrical motors that are the most diffused actuators in nowadays industrial robots. And we will talk about transmission, that are the way that you map your actuator, you adapt your actuator capability to the system that you want to actuate. For example, if you want to have a high torque and you don't have enough torque in your motor, electrical motor, you might want to use a reduction gearbox to amplify the torque. And then finally, we will discuss about some non-idealities in the actuation systems. And finally, doing a simulation, how to perform a simulation of an actuation system, in particular of a DC motor that we will use then in our first lab of control. So the simulation will be just open loop simulation, free motion of our actuator, while in the lab we will close the loop with the controller and the actuator together. The actuator is a device that produces motion, can be defined like that. This motion can be linear or angular, in case of rotary actuators. And the output of an actuator would be linear angular velocity, in case we consider the actuator as a velocity source, or a force or a torque, in case we consider our actuator a torque source. And what we will consider in our course is actuators as force torque source. But there are other approaches that we consider the actuators as velocity source. We don't care about that because in this course, we will define models of the robot, that rigid body models that wants force as input and provide acceleration as output. And since they want force as input, it's more convenient to consider actuators as force and torque sources. There are different kinds of actuators that are used in robotics. One is the pneumatic actuators. Other class of actuators are hydraulic actuators, electrical, as we discussed, and more exotic ones like HSA, AHA, EHA, and series elastic actuators and piezoelectric. So actuators are the devices through which the controller acts on the system. We saw the sketch before, and they are used to map a low power control signal, typically electrical, using some supply power that could be, again, electrical, hydraulic, or pneumatic, and create a high power control signal that transmits some mechanical power through the transmission to our system that we want to control. And there are power losses as well due to dissipative effects that are present both in the actuation as in the transmission and in the system, that are, for example, due to friction or joule losses in the electrical motors. And okay, so this is mechanical power that we want to convert from electrical power, for example. And the power is can be defined as the product between different quantities. Normally, it's, if consider a power flow approach, you have an effort variable and a flow variable. In the case of an electrical domain, the power is defined as voltage times current, where voltage is the effort variable and current is the flow variable. In the hydraulic domain, you have power expressed as flow rate and pressure times pressure. And in the mechanical domain, you have force times speed. And the mechanical domain defined as a rotational motion. Again, you have equivalent torque and angular velocity, angular speed. And the power, it's always expressed in the watt SI unit. while we can define efficiency as the ratio between the, sorry, this is an error, power output divided by power input. We're correcting the slide. And the energy or the work is power times time, and it's measured in watt hours, joule. So the actuators in robotics, they have different requirements, and the most important one is to have a high power to weight ratio, because we want to have low weights in the actuators and low inertia, because we want to be able to move our link, but we don't want to increase the mass and the inertia of that link, because in that case, we will need more power to move the link. And in the case of a mobile robot, this is it's a requirement. It's super important, because the mobile robot needs to carry around his own weight. So reducing the inertia of the link and of the actuator, it's important, because it will have less requirement in terms of energy from the battery, for example. And we see also that the inertia of the rotor of a DC motor affects the inertia of the link. And then we want to have the possibility to have overloads sometimes and delivery very impulse torques. Why? Because we want to have high accelerations. We don't want to go a constant motion. Normally we want to move the end effector from one place to the other. And the best way to do that is to accelerate as fast as you can till the middle of the trajectory, and decelerate as fast as you can, because normally you want to do this motion quick. So we want to deal with high accelerations. We want a large range of rotational velocities, because we want to move accurately, slow, whenever we perform machining operation, for example, or we want to move quickly when you move from one point to the other of the workspace. And we want also high accuracy in position. Normally, it's 1/1000 of a cycle, 1/1000th of a cycle. This looks like a low accuracy, but if you think about whatever we discussed today, that transforming this rotational motion, there was a question at the beginning of the lecture about transmission that transform a rotational motion into a linear motion with a lead screw. We see that, and then if we measure the positioning on the motor, we will have a very high accuracy because of the reduction ratio on the linear motion. Then we want a low torque ripple. We will see that in a DC motor or in synchronous motors, we have ripples in the torque generation that can create vibration at low speed, and we want to reduce that. And also the power is a requirement that can be very different. In case the robot needs to interact with a human, the power needs to be limited to 80 watts, or we can have very big industrial robot that moves around cars that goes up to 10 kilowatts. In that case, you don't want to get close to this robot, and normally they are located inside a big cage, inaccessible by the humans. And the first pneumatic kind of actuator we describe is pneumatic motors. The source of power in here is a compressed air. So there is a compressor that compresses the air and provides some pressure. And then this pressure is turned into mechanical energy by means of the pump normally works, or the compressor works with pistons and turbines, and provides high pressure. And This high pressure, it's transformed into mechanical energy by means of valves. I will correct the slides. Opening the valve, you can move the pistons in one direction or the other, and the pneumatics motors are difficult to control accurately because the fluid compress. So because of fluid compressibility, it's hard to have an accurate positioning, and also to have a fast reaction because you have usually you have slow transient. So whatever you use pneumatic motors for, pneumatic actuators for, is for low force application that requires intrinsic compliance. For example, when you are grasping an object on a conveyor belt or opening close the grippers. Normally the grippers are actuated with pneumatic actuators. You can have some examples of pneumatic motors. From Festo company, like this example it's an arm, and you also see here an application for pulling up loads. They can be very powerful with this origami arrangement. The two audios are overlapping now. So they can extend or compress, and you can use this for pulling loads. And an example of a pneumatic actuator is a McKibben actuator, which is a pneumatic muscle that compresses and extends exactly like a muscle, a human muscle, and creating pressure. There is this braid of interleaved, twisted bladder element that when it inflates, it contracts. So if you pressurize, it contracts. When it depressurize, it extends. And of course, the extension is passive. So normally you use these muscles in an antagonistic way, such that whenever one compresses, the other relaxes, and the other way around. And I did a work on this back in 2010, using this for in a system to check, characterize these kind of muscles using air and water and see how they're behaving. And why we want to use fluidic muscles? Because they are lightweight, they have no gears, no backlash, and they can change both position and stiffness. So by co-contracting these two antagonistic actuators, you can either stiffening the link motion, make the link stiffer, or you can move the link. So if you co-contract, you increase the stiffness. If you contract and one and relax the other, you move the link. And they tolerate misalignments. That's another point. While hydraulic motors, actuators are similar to pneumatic actuators. The difference is that they employ oil and not air, and oil usually is considered uncompressible. So the bandwidth of an hydraulic actuator is much higher than a pneumatic actuator, because whenever you pressurize the oil in one point, the pressure wave is propagated instantaneously in all the places where the oil is. And the idea of hydraulic actuators is very similar to the pneumatic ones. Instead of a compressor, we have a pump that pressurizes the oil coming from an accumulation tank. And this pump creates a pressure, and then the mechanical energy is obtained by means of valves. And we see here the pressure, oil in pressure coming from the pump, and then moving the valve, we pressurize either gist chamber of the piston, or moving the valve in the other side, we pressurize the other chamber of the piston. And if in general, if one chamber is pressurized, the other chamber is connected back to the tank at zero pressure, because normally it's at atmospheric pressure. And the difference in pressure is the one that creates the force on the piston rod and moves the piston one side on the other. Now, you can have linear pistons like this that are called, linear hydraulic actuators that are called hydraulic cylinders. And you can have also rotational hydraulic actuators, or called hydraulic motor or rotary actuators. That is like a piston with two chambers, but the chambers are on a circumference, so they are not linear one. There is a vein that separates the two chambers that makes the same effect of a piston rod that moves on one side or the other, changing the position of the shaft connected to the rotary actuator. We use this rotary actuator in the robot, but they are not very good because they suffer a lot because of friction and of leakage. Leakage is whenever you have oil passing from one chamber to the other, because you cannot have a perfect seal here. But achieving a good seal in a linear piston is much easier than in these guys. So you have a constant leakage from the high pressure chamber, that normally is the red one, to the low pressure one. So these guys are very inefficient. And the advantages of hydraulic actuator is the very high power to weight ratio. So you can have, instead of we see in electric motors, wherever you have, if you want high torque, you necessarily normally have low speed. In hydraulic, you can have both high torque and high speed, and in a very small and compact element. So a piston in our robot weighs like 1.5 kilograms and produce like 6,000 or 4,000 Newton force and a very 10 Newton meter speed. So super high power and very low weight. They have no static overheating like in the electrical motors. They are self-lubricated because we have oil. They are inherently safe. They don't have sparks like in electrical motors. They also, as I said, large torque, large velocity, and passive compliance. This is related to the fact that the oil is ideally uncompressible, but it has some level of compressibility. And this compressibility makes such that if you get an impact in our actuation system, in our for example link, the oil compliance, the pressure increase locally in the oil because of the compressibility, and the oil compliance mitigates and dumps this impact force without transmitting it to the structure. That will create fatigue on the structure after a while. If you think about an electrical robot, a legged robot walking on the ground, you have continuously impact with the ground. You need to dump out this impact. Otherwise, after a while, your robot will fall apart and break because of fatigue. So fatigue is whenever you have a constant mechanical load, even small, that is hitting your structure, and after a while, your structure can damage. Disadvantages of hydraulic is that they need an external pump and they need an hydraulic supply. They're harder to control because they are non-linear. You have a flow, a non-linear relationship that relates the flow and pressure with your valve opening, and they are large size. Usually, it's very difficult to have small pistons, small hydraulic actuators. They have low efficiency. The low efficiency is related to the fact that you have friction losses due to the valves. So if you have your supply pressure at 180 bars, for example, fixed, and you want to create a very low force on your actuator, you close the valve and you drop most of the pressure across the valve. So you waste a lot of energy that you don't use in the load. And you recirculate oil through the pump as well. So they are not efficient, and they have a high cost and increased maintenance, because sometimes the oil leaks, you have drops of oil all around, and they're problematic in this sense. But they are useful for heavy load applications that for which electrical motors will not be powerful enough, or at least you will need very big motors. And I can give you 2 examples of these heavy-duty applications. This is an experiment we did back in 2017 with our hydraulic robot called IQ-Real. And as a power of an example of the power of this robot, we were pulling an airplane of the weight of 3 tons. To do so, the robot has to deliver a pulling force, horizontal one, of more than 900 Newton to overcome the static friction on the wheels. And this was possible only with hydraulic actuators. The other are the Boston Dynamics Atlas that was able to perform very, very accurate and fast motion with this 70, 80 kilogram robot. Certainly you saw this video, and this is incredible example of control accuracy, and also very accurate and fast positioning of the joints. And while in terms of electrical motors, I think we are going beyond time. So I think we should continue from this point on the next lecture. And if you have any questions, we can ask. Okay. So see you tomorrow afternoon, and sorry for the delay of today and the repetition of of the first part of the class. If you have any question, you can write me an email as well, and I will try to understand and put the videos on the Moodle so that you can see. Okay, bye.